for Microsoft. I work in our retail and consumer goods division, which is different since many of you might know me, know that I worked in the public sector in the DC area for a long time. But nonetheless, my career spans 25 years or so with Microsoft Technologies, working for a variety of Microsoft partners like Avanade and a bunch of other people who uh, provide services to the federal government. And this is my second go around at Microsoft. I worked for Microsoft Consulting Services the first time, working with said government work, and now I'm a cloud solution architect. All along, though, I've been a developer. I like authoring software, and I've also had a very keen centricity around data. So uh, I've been expert with the SQL Server platform, and especially with our business intelligence suite. I got engaged with that before it was ever even released with the Yukon release in 2005. And it was a natural segue into performing predictive analytics. So, as many of you know, maybe in the past 7 or 8 years, cloud computing and the advent of, massively parallel processing compute systems and the explosion of data since, we've been talking about big data probably since maybe 2006 or seven. And that it's really gotten to the point where those two things came together. The compute platforms and the proliferance of data has really enabled the development of highly effective predictive analytic software packages. And Microsoft really behind the scenes has been at the forefront of that in their research and R&D department, Microsoft Research. We're going to spend a little time today talking about some of the packages that they have produced. They are not absolutely bound to running them in Azure and Azure Machine Learning Services, but they certainly are highly integrated with Azure Machine Learning Services. So in some cases, the visualizations that are produced can be uploaded into the Azure Machine Learning portal so that those people who are either developing the machine learning models and doing a lot of the compute in the cloud, or people who are charged with managing those models can go in and view some of the visualizations and gain a lot of information about the inner workings of the machine learning services that have been deployed. And so this is just a giant topic. It's deep and it's broad. And to say the least, it's really very ambitious that I think I'm going to cover it in less than an hour. But, I love a good challenge, and I'm kind of a knucklehead too. So here we go. As I like to do, I like to start with what the problem is. Well, the problem is that traditionally, kind of, I'll say historically maybe, data scientists find themselves working in the dark. And one of the quotes that's kind of pithy is that machines learn in the darkness and data scientists struggle in the void to explain them. But to the consumer of a machine learning service or person who is subject to the decisions made by a machine learning system, they would ask the question, well, why should I trust you? Why should I trust the machine? Why should I trust the developer of the machine? And so, even as a developer of machine learning models, a data scientist, you ask yourself, well, okay, I got this model and I trained it on a bunch of data and it's starting to make predictions. And I did some, some evaluations, testing the predictions against known outcomes. And, I hopefully have a model that has a high level of efficacy. I use that word because accuracy is taken. It's actually a specific metric you're probably familiar with. But I ask, why does my model predict that particular outcome? Tell me why. How could I ensure that the predictions my model are making are correct? I mean, just because my evaluations tell me that it's a highly effective model, it doesn't necessarily mean that the predictions are correct. It just means that they match the known outcomes that I gave them when I performed the test. But machine learning models are tricky little creatures. They have this ability to find shortcuts hidden in data. They have this ability to act to spurious correlations. And so I don't even know whether they're correct or not. How do I ensure that? And in doing so, what evidence would I be able to gather to justify these predictions to say somebody who's subject to their decisions? Uh, if I find that I don't have correct, I'm doing my evaluations and I see that the predictions aren't correct, or if I'm using the model in production and I'm finding that it's making erroneous predictions, how can I find out what that cause is? Um, how would my model's predictions change if I alter its input? Now, that's a fun one because, as we're going to discuss later on, altering the data is often one of the most effective ways of sleuthing our way through what the machine learning model is actually doing. So now that we have a little idea of our problem, what are we going to do about it? Well, ta-da, the solution is, of course, let there be light. So at the end of the day, data scientists absolutely must be empowered to build interpretable and explainable and ethical AI systems. They have to be responsible. And so at Microsoft Research, they laid out a series of responsible AI principles. And so, I'll do the eye chart thing here a little bit. It has to be understandable. I mean, it can't be this opaque black box that says, because I said so, especially if it's wrong or if it's reinforcing biases, which leads us to the fact that it has to be fair. It has to treat all people fairly and not reinforce biases or stereotypes, because that would be a really bad thing. It has to be inclusive. It can't be, restricting access to opportunities and resources based on bias that's hidden in the training data and finds its way to quietly influencing the predictions that the model makes. Think about people applying for loans, for mortgages. Think about people, who are in prison and are just trying to get on parole. Not that we all want them out on the street, but if they truly are reformed and are deserving of second chance, we don't want to just keep them locked up for no justifiable reason. Healthcare is very important. We're using machine learning models in healthcare. What if it's based on some stupid bias the country of origin or their financial capability to pay, deciding what kind of medicines and treatments they are going to have prescribed for them and what might be withheld from them. This is a huge ethical dilemma when fielding AI systems. They need to be accountable. I mean, if they make a spurious prediction, somebody's got to be held responsible to it. And there's got to be a way to circumvent an erroneous prediction. And ultimately, also, when we talk, you can't even say IT without saying there needs to be privacy and security. But you have to safeguard people and their data if they're applying for services or if it's their medical history or any other identifiable information. We're not going to talk too much about privacy and security because it's kind of an outrigger topic, but it would be unfair not to touch on it a little bit. So when we talk about responsible AI, we are talking about building ethical, trustworthy AI systems. We need to be able to mitigate inequities by being able to look into the inner working of a machine learning model, the ability to explain how the decisions were derived and why they were made. Because bias in AI systems, as we have already discussed, can result in unintended consequences. So we have sort of this trifecta that we discuss at Microsoft around the topic of responsible machine learning and AI. And one of those spokes, the key one that we're probably going to discuss here today, is how do we understand machine learning models? How do we interpret and explain model behavior? And we're going to discuss the difference there as we move forward. How do we potentially assess and mitigate unfairness? How do we find out if something's going wrong under the hood and find a way to prevent that from happening? How do we protect people and their data? And you could probably fill that in with a lot of standard IT stuff. Privacy, confidentiality are generally networking issues and data security issues and encryption issues. So, you could probably fill that in. But ultimately, we also need to be able to control the entire end-to-end machine learning development process. We need to be able to document what was done so that if somebody does have a question about, okay, how did you build this? What inputs were determined to be the most influential to the outcome? Where were some of the thresholds and the values of those features? And by the way, for those of you who are primarily database people and not machine learning people, we talk about features, and those are columns if we're talking about tabular data. And we talk about observations, and those are transactions or rows in a table. So we have to be able to document what values in specific columns were thresholds or cutoffs when we determine, say, a binary classification job, yes or no. So when we talk about explainable AI, there, of course, are motivations. Why are we doing this, and how do we apply it? And there's many of them. Some don't always seem obvious. And one of them is the actual development process itself, the ability to debug and explore what's going on in the models as we're developing them. And you'll find that some of the better explainability and interpretability modeling algorithms out there were actually created not out of the sense of social responsibility, but because the people developing the models were frustrated by the fact that the model was learning shortcuts and identifying spurious features. And, even though the model came out and evaluated very highly through traditional accepted methods like cross-validation, they were still, essentially on closer inspection providing erroneous predictions. And so these packages, these algorithms have been developed just to help in developing the model. Then, of course, as we talked, the human AI collaboration. I mean, we need to be able to produce an explainable prediction for customers, for people making decisions. If many of you may be in the DC area and you might be working for some three-letter agency, and whether it's civilian or military or otherwise, they may be making decisions that that are life or death decisions for people, whether they have to do with healthcare and other civilian notions, or whether we're making decisions about our military servicemen and women downstream, and whether or not they're being deployed into safe situations. There's a lot of opportunity for human interaction with these systems. And so these are some practical applications and, again, motivations. Now, there's probably not an industry out there that isn't impacted some way, shape, or form through regulatory compliance, whether it's PCI, whether it's GDPR, whether it's HIPAA, whether it's anything else. You have to be able to explain what's going on in these models. You need to be able to support mandates around anti-discrimination and equal opportunity. You've got to be able to mitigate these risks, especially if, like, these AI systems are predicting, intrusion detection systems and things like that. There's risk management there. Of course, risk management also pertains to safeguarding the data that we've discussed. And then, there are people making scientific discoveries using machine learning services. They may never publish or deploy the machine learning model as a service, but they're using it to do research for detecting, the structure of COVID-19 and whether it's morphed or not, or discovering, doing cancer research or DNA research, or things that, quite frankly, go over my head, and I'm just too dumb to understand. But there are people out there using machine learning for those purposes, and just like for the machine learning developer, they may not be publishing the model, but they need to understand what's going on. They're pure data scientists, if you will, subject matter specific data scientists. So these are some of obviously the motivations behind this trend towards explainable and responsible AI. So now we're going to dive straight into interpretability and explainability. And the clue here for the observant is that we're understanding machine learning models and their predictions. So a lot of people use these two terms interchangeably, and there are probably some people with better credentials than I that would argue this. It could turn into, if you will, some sort of a religious conversation about what they believe. But this is sort of according to my research and my opinion, if you will. I think it's good to be able to separate these two terms. Interpretability goes along with the term you're going to hear quite a bit, which is global. And it pertains to the model itself, not to an individual decision or prediction that model made, but to the entire model. When we develop a machine learning model, we'll often discuss a concept called generalization, which means that we haven't fit the model's predictive capability too closely to a specific sample of data, but rather that model has been trained in such a way that it can cope effectively with new data, even if it contains values that had not been seen previously or were not taken into account during training time. Explainability, on the other hand, pertains to the individual predictions themselves. Global, the functioning of the entire model. Local, why did you decline me for my loan? Why did you prescribe me this medicine and not that one? Why did you, etc.? And so on the side of interpretability, humans are just more likely to trust systems that can justify their decisions. And therefore, the goal of the model's owner or creator is to produce and promote that trust in its capabilities. Nobody wants to, go say to their lending institution and fill out an application online and get an automatic response, no, and then not get any understanding of what about them disqualifies them for this loan. And so it really has to do with inspecting the entire model's implementation, the source code, if you will, to gain an understanding of how it makes its decisions, what algorithms were found to be the most accurate, the most ethical, and ultimately just to comprehend the rationale behind not one, but all of its decisions, how it makes decisions. And on the explainability side, the degree to which a human can identify that rationale is what we're talking about. And the goal is not the creator or owner, but the subject to understand why that prediction was made, why that behavior is justifiable. And rather than occurring during the development of the machine learning model, explainability pertains, at least in my opinion, to post hoc analysis of the model's predictions. And, of course, to explain why those decisions were made and how it led to the decision that was made. So kind of want to lay that out a little bit because I will probably make specific reference to one term or the other, and it's important that at least you understand my frame of reference. So that leads us again to a couple of use cases. We ask, hey, we need to be able to explain predictions. We need to be able to assess the quality of the model and how well it's fit during the development. We need to be able to identify which factors had the most influence on those predictions and how did each one of those features influence an individual prediction. And then, of course, not all features are independent. Sometimes there are interactions that are greatly influential on the prediction, the inference that was made by the model. So under all of these situations, the libraries we're going to discuss are very useful. Another sort of upfront thing is to understand some really basic fundamental algorithm differences. We'll talk about linear models, and generally speaking, they're kind of based on regression, although there are linear models like logistic regression that are tuned for classification jobs. And they generally ask the question, how does an input relate to an outcome? How do they correlate? And in this little visualization I'm showing you here, we have the number of incidents on the horizontal or x-axis and how it correlates to the number of officers that are dispatched to a scene. And some of the inputs might be the neighborhood that's in, the time of day or night it is, things like that. But ultimately, we want to know where were more than one or two or even three officers dispatched and why. I'm sure you've seen somebody pulled over on the side of the road at some point and like, what were they doing? They speeding and they got 6 cops around them. You just wonder, does it really take 6 cops to write a ticket? You know, you got to wonder, it's the screw in a light bulb scenario. But here, you know, what we're doing is we're seeing that in this particular instance, there is a very strong, clear positive correlation between the number of incidents and the number of officers. Then there are tree-based models, and we could associate them primarily with classification. But once again, tree-based models are also effective, and there are versions of tree-based models to handle regression jobs. And they work a little bit better in situations where there are correlations, dependencies. Linear models work great when there's a great level of independence between all of the X, all of the columns in the database, except for each one of those columns correlation to the target, Y, the outcome, the prediction that we need to make. So when we find that X, you know, the sum of X, there's a bunch of different variables, let's say a table with 10 different columns. When we find that there are strong correlations between all of those columns or between certain columns other than their correlation to Y, or that maybe X1 has very little correlation to Y and X2 has very little correlation to Y, but when X2 interacts with X1, then there's a strong correlation with Y. Those scenarios are better handled by tree-based models. And so they work like a fundamental dialectic. You ask a question, you get a yes or no. There may be a series of follow-up questions. We call that depth. And what's happening here is that they're segmenting the training data, if you will, into smaller and smaller subsets until you can see the discrete differences between them and make associations between the outcomes. So just kind of laying that out there, we're going to talk about the difference between Glassbox models and Blackbox models. And so the choice of that algorithm that you use can have a very profound impact on what we'll call the transparency of the model, or the, since we're talking about the model, you know, whether you can understand the internal workings of that model. Simple algorithms, you know, as you might imagine, are far easier to understand than complex algorithms, and it thereby makes it easier to understand the predictions or the inferences that were made. And referring to what we just saw on the previous slide, things like linear and logistic regression and decision trees and naive Bayes and k-nearest neighbors, they're very easy to understand. You can see what happened without any other programmatic juggling. You could just see how you can inspect the internal workings of the models. Blackbox models, including things like, you know, you've heard of neural networks and convolutional neural networks and residual neural networks, and these far more complex and opaque algorithms support vector machines, ensembles of models where, you know, not just one modeling algorithm, but the output of a combination of modeling algorithms combined produce a higher performing model, but their complexity makes it very difficult to tell what's going on inside. Random forest, which is an ensemble of decision trees. It may be easy to see what happened in one decision tree, but if you're doing a Monte Carlo ensemble involving tens of thousands, maybe random of decision trees, and summing them up and finding, the mean or the average or the median or whatever you choose as your, what's going on inside the random forest algorithm, it's really complex and it's difficult to understand. A book that I'll point you to in the reference is written by Christoph Molinar. It's kind of seminal in this realm of interpretability and explainability and responsible AI. He says the higher the interpretability of a machine learning model, the easier it is for someone to comprehend why these decisions and predictions have been made, and that's clear and simple. So there's also a notion, and they correspond directly with Glassbox and Blackbox, is whether or not we can achieve interpretability before or during the training or after training. And the Glassbox models, being more transparent, the ability to determine what's going on and how they make their decisions is intrinsic to the model. What we're doing here explicitly is restricting the complexity of the model itself in order to make sure that it's readily understandable to a human being. And this is achieved by way of its inherent level of interpretability and complexity. When we look at black box models, just as the term implies, you look at it, it's opaque, you have no idea what's going on inside the magic box. We have to do a post hoc inspection of those models. We have to probe the model in certain ways to find out how it makes its predictions, because just looking at it functioning in the real world, if you will, isn't sufficient. And these are, of course, applied, these methods are applied after you train the model and deploy it. It could be actually in production. And we generally achieve this through what we call explainers, models that are trained around the model that's the subject. Generally speaking, we train a Glassbox model, a model that's simple to understand based on our analysis of the black box model. And generally speaking, these are model agnostic. So in other words, it doesn't matter what algorithms were used in the development of the black box model. And in some cases, it doesn't even matter what modeling algorithm is being used by the explainer. Like I said at the beginning, this is a very deep topic and it's ambitious to try to even tackle it, but I'll try to keep moving along. Microsoft has produced a number of packages. We're only going to focus on the first two of them, Interpretable and Fairlearn. Smart Noise and Seal are all about the data privacy and security. But I want to mention them because they're part of our suite of responsible AI tools. And Interpretable, as it sounds, is for inspecting feature interactions and measuring the importance of features and understanding models. And there's a variety of methods in that package. And Fairlearn is really dedicated to assessing and mitigating unintended bias and rectifying unfair decisions, and in that sense, building trust with people, justifying the model's predictions. So in the Interpretable package, we have Glassbox methods and Blackbox methods, just as that's why I had that other slide. And so these have primarily been developed by Microsoft Research. Explainable Boosting Machine is the product of Microsoft Researcher. Linear models, decision trees, and decision rules, as we said, are inherently transparent and inherently interpretable, easily understood by human beings, and they are not necessarily specific intellectual property of Microsoft, but they are methods in the Interpretable package. And then there are black box methods like SHAP and LIME. SHAP and LIME and Morris sensitivity analysis are actually the product of Microsoft Research, Microsoft researchers. And so even though they're widely used, and some people might even tell you that they're open source and they're community, they're actually have their origins in Microsoft research. And um, partial dependence is kind of a well-known technique. You can find partial dependence algorithms in common machine learning packages like scikit-learn, et cetera. But Microsoft has its own implementation as part of the Interpretable package. And so there's a link down there to give you an idea and a reference to some Microsoft works out there so you could read up on that. And that's part of the slide deck for you later on. So let's discuss EBM, the Explainable Boosting Machine. So this is, of course, one of our tools for implementing responsible AI, and it is an intrinsically interpretable Glassbox model that was developed at Microsoft Research, and it builds on the idea of generalized additive models. It's a tree-based, it uses cyclic gradient boosting, and I'm going to give you an intuition for how that works. It automatically detects those interactions that we were talking about. So it ends up performing as well as state-of-the-art techniques like those random forest and gradient boosted machines, which are black box models, but it's transparent, it's easy to interpret. And that's really a breakthrough that you can get the performance that you would normally associate with more complicated models like random forests and GBMs, but you get it in an easy to understand package, something like a decision tree or whatnot, or a linear model. Unlike black box models, they produce lossless explanations. We can truly understand why they did what they did, why they made their decisions. You can justify specific inferences. They're also very compact computationally, mostly at prediction time. EBMs can be a little bit slower than some of their competitors at training time, but the trade-off is, of course, that you don't have to do anything else to understand what happened in the model. But when you deploy them into production, they render inferences very, very quickly and are very memory and CPU efficient. So what the heck is an EBM and how does it work? So let's think of a data set, a training data set that has a number of different features. N, I don't know how many that is. It could be 5, it could be 15, it could be 32,676, whatever that may be. So the idea of a random forest is to compile a bunch of different decision trees, but the way it's traditionally done in a random forest algorithm, which is the basis for, it's a tree-based algorithm. It's the basis for gradient boosted machines and ADA boosted decision trees. They're more complex models based on the concept of a decision tree, but the EBM takes an iterative approach. So on our first iteration, we're going to train a very small decision tree that is only capable of looking at feature 1 in this case. It doesn't look at any other features or any other interactions. It's a very shallow training run. And then in boosting fashion, we're going to update the residual and pass it along to the second tree that is being trained only on feature 2. And we're going to take its residuals and pass them on to the third feature. And again, the third feature only looks at that one feature, that one column, that one parameter. And then it passes its residual on and so on and so on until we reach the last feature. And then we pass its residuals on to a second iteration. And it trains only one shallow tree on feature 1, passes the residuals to 2, shallow little tree on 2, passes the residuals to 3, and so on until we do a third iteration, a fourth iteration, a fifth iteration, n number of iterations. It could be 5,000 or 10,000 iterations until the model converges. And then we have all of these trees, separate trees, shallow little trees, easily understood little simple decision points, trained on the sample data for only that feature, with their residuals being passed forward The residual is the error, what's left over, if you will, to the next one, to be understood by the next feature. And then what we do is we build a vector or a graph based on all of the data that we determined for feature one, all those little decision points, all those little predictions, if you will. They're not really predictions, they're analyses of the training data. And they can be used to plot a graph because all they are is a series of decisions. And once we have that vector, we can just get rid of all of those trees. And then we can go on and we can add the second feature. And once we have its vector, its little graph, we can get rid of all of its decision trees too. We don't need the work. We only need the answers. And so we do the same thing with feature 3 and so on until we finally have nothing but a series of vectors. And these series of vectors are the decisions. They are the model. And they are intrinsically understood just by looking at them because they are nothing but simple, a series of simple decision trees with each trained decision point mapped out in a series of data, a vector. So the next algorithm, and we kind of touched on it already, I'm even using the very same linear graph. This is basic Cartesian algebra, mapping X and Y coordinates across a graph. And linear models are very easy to understand, the dependence between a target and some features. And there's a very simple algorithm where the target is equal to the sum of the weighted input features plus errors. And it's very easy to understand and interpret. So it's one of our Glassbox models, our flavor of it, if you will, in the Interpretable package. There are also decision tree and decision rule algorithms in Interpretable. And the decision tree, of course, creates these multiple subsets of the data by splitting it along a cutoff value, some kind of a threshold in those features that prove to be highly correlative to the target. And it performs well, again, where the feature to target relationships aren't as linear or where there are strong feature interactions, where there are where independence of X cannot be assumed. So a simple example is, hey, the temperature, your body temperature is the feature. Do you have a fever? Oh, I don't know. Well, if it's greater than 102, there's a threshold. If it's not 102 or more, then just stay home. It's no big deal. But if it's greater than 102, then you got to go to the hospital because, you might burn up. That's not a good thing. Otherwise, don't worry, stay home. Decision rules are just like all of the programming any programmer's ever done. We used to call this symbolic AI. It's intelligence that is encoded by human beings using simple if-then statements that consist of some sort of a condition. If the condition exists, then do this, otherwise do that. So let's ask the question, will it rain tomorrow? Well, did it rain today? Might be our first question. And this is simple Bayesian logic. And is the month April or May? And if both of these evaluate to true, then yes, we predict it's going to rain tomorrow. If both of them are not evaluating to true, then maybe the prediction would be false or no. We're going to move on to another complex algorithm called SHAP, or Shapley Additive Explanations. And again, it's a product of Microsoft Research, it's based on game theory, pioneered by a guy named Lloyd Shapley, who, by the way, is a Nobel Prize winning laureate. I think he got his Nobel Prize in game theory in 2012 or something like that. And Shapley additive explanations are model agnostic. However, they work more efficiently on certain types of classes like tree ensembles. And they measure how much each feature contributes to a prediction as compared to what we call an average prediction. So predictions can be explained by assuming that each feature is like a player in a game and the prediction itself is the payout. And so Shapley values, Shapley additive explanations is based on an idea of Shapley values. They determine how to fairly distribute the payout among the features in the training data set. And so let's take a look at how this works. So let's just say we're talking about a loan application process. And this guy named Bob wants a loan. Well, we don't start with, let's just say we're, applying a scoring type of algorithm. We don't assume zero. Like, we assume an average. Maybe. There's a number of different ways to do this, but for the sake of our example, we're just going to establish a base rate. And what we're saying is that when we've inspected a training data set, a sample, and let's just assume that the classes were evenly distributed, like 50% of them were people who successfully paid off the loan, and 50% of them were people who defaulted on their loan or were delinquent in their payments one or more times. And we came up with the average rate for successful payoff based on the questions in the loan application. That's 16%. So Bob here, he fills out his application and boink, he gets a prediction of 22 and he gets declined for the loan. Now, Bob's not a happy camper. He wants to know, hey, I'm not a bad guy. I've been through this process before. Why did you decline my loan? And so we have to ask, how do we get all the way here from 16 to 22%? How do we justify that? Well, that Shapley additive explanations takes a little bit of an algorithm here. It's additive. This is where you're going to see the additive working. First, without looking at his application, we know absolutely nothing about Bob. We haven't inspected the values in any of the answers that he provided in his application. We just start at that base rate of 16%, assuming we can either deny or confirm whether Bob is going to pay off a loan. And so that is the expected prediction, the first feature, if you will. And then we're going to ask the question, can you tell me how much you make and can we verify that? And we are unable to do so. So we don't know how much Bob makes. We don't even know whether he's verifiably employed. So that bumps him up to 18.2% in our scale. And that's not good for Bob right there. So then we take a look at the next question in his application, which is what's your debt to income ratio? And maybe we extrapolate that based on saying, hey, Bob, tell me all your debts. And then we go back and say, well, we can't even verify his income. So that's kind of an automatic bad answer right there. His debt to income ratio is a little more severe than we would like. And that shoves him all the way up to 21%. And that's really not very good. And then we see that Bob has actually been delinquent on one or more payments in the last 10 months. And that pushes him all the way up to 22.5% or almost 23% here. Then we go to the next question and we ask, have you opened any new recent accounts? And he has not. Now, that's kind of a loaded thing because he doesn't have any new accounts. So that means, he has foreseeably not been applying for loans, but maybe he's been turned down for loans. We don't know that. We just know that he has no recent accounts that were opened. All of his existing debts are longer term debts. So that pushes him back down to 18.5%. And, we might even have determined that we would approve his loan there. But then we look at a final question and it says that Bob has a 46-year credit history. Now our intuition might tell us that's not a bad thing at all. He has a long credit history, but simple math tells you that assuming his credit history started maybe when he was 18 years old, Bob's like 64 or 65 years old. And I can tell you that they don't hand out loans for retirement. And maybe they're just saying, hey, we don't think you're going to be alive long enough to pay off this loan. You're a bad risk. Now, the problem there is that age is a protected classification. And you can't really tell somebody that they're too old to be the recipient of a loan. So this kind of shows you how Shapley additive explanations can perform a post hoc analysis of a black box model and understand, based on the questions, how that inference came to be, explain its rationale and logic. The next thing we're going to talk about is LIME, or locally interpretable model agnostic explanations. That is a mouthful. And what they do is they interpret black box models by using a local surrogate model. And what that means is we train a transparent model on a specific set of information that pertains to a specific decision or a specific prediction or inference. And these local surrogate models are typically developed using easily interpretable algorithms like linear regression, linear class, logistic regression, which is classification, or decision trees, things that are easy to understand. And they explain those individual predictions that were made by a black box model. And we find, or it has been found, that even a simple linear model can provide a very good approximation or a good understanding of a very opaque and complex black box model's behavior. So what LIME does is it fits this simpler model around what we call the local neighborhood of the prediction, or the information pertaining or that's very close and adjacent to the data that influenced that prediction, a very narrow or local decision space. And then what it does is it perturbs or it modifies the individual data points, and it uses that to generate synthetic data. Then it uses that synthetic data to evaluate the black box system and ultimately to use to train the Glassbox or the surrogate model that we can use as a means to interpreting what happened in the black box model. And as I discussed earlier, its inventor actually came to develop this algorithm because he had a model that was, that he trained and got a very high level of efficacy from, but it was producing erroneous predictions because it was making spurious correlations between certain things. It was taking shortcuts. It learned some of the variation of the data that in his case, how the data was being collected rather than what the data was itself. And it was making biased decisions. So anyway, LIME will enable you to interpret this explanation in the same way you would reason about this simpler linear model, because you're actually at the end of the day, explaining a simple linear model. It's just that the data that model was trained on has a direct correlation to the data that was the behaviors inside the black box model. So just to give you a little visualization for LIME, here we have a random forest model's output. It's a simple binary classification job where positive or 1 are the dark areas and 0 or negative are the light areas. And you could say that dark would be yes, give them a loan, and 0 light would be don't give them a loan. And the predictions in this case on this graph are for just 2 features out of the entire feature set, feature 1 and feature 2, whatever they are. So what we're going to do here is select the local instance of interest, the decision or the prediction that we're interested in justifying. And then what we're going to do is we're going to modify the data. We use the term perturb the data set and get black box predictions for these new data points. And those are represented by all these little black data points. And then we weight the new samples according to their proximity to the instance of interest. So there's a greater weight to the points that are close to that decision that we're at, the prediction that we're interested in. And then we can train a weighted, more interpretable model based on that data set of those variations and explain the prediction by interpreting the local model, this new transparent model. And so what we can see here is that all of the negative signs, or which are to the, in this case, to the right of a decision boundary. And it's maybe not easy to see, but there's a white line there along the right edge of the blue or the light area, and that's everything on the left of it is positive, and everything on the right of it is negative. And so it's basically telling you how this model behaves. what it's basically saying is that the white line says that the probability of it being class 1 or positive is the same as a random coin toss. So that's the place where anything to the right would be negative, anything to the left would be positive. And I don't know if that helps, but that's kind of the way Lime works. None of this stuff is easy to understand. I'm interested in if this actually manages to help you understand these things. So I'm open to your feedback. You know, you can get that to me via email or LinkedIn or however you want. But not easy to understand all these things. The next thing we do, as I mentioned, our Interpretable includes a proprietary algorithm for partial dependence plots. And they basically let you see how the values in specific features correlate to an outcome. And what we can see is that it can either be linear relationships where, like, as the value of X rises from 0 to 6, so too does its correlation to the value and the target on the y-axis. One goes up along with the other. We might see that there's a monotonic relationship where, you know, there's no variance due to the values in that feature, but that feature itself has correlated pretty consistently with a specific value on the y coordinate. In this case, it's 0.6. And it can also model a complex relationship, or it can show you, if you will, a signal that in this case, there is a strong negative correlation from values 0 through 4, at which point it flattens out temporarily and then makes a severe drop at the value of 6, but then starts to climb after you reach 7. We don't know what happens after that, but that's sort of like a heartbeat. We can see that the value of that specific variable has a strong correlation on the outcome. So to better understand partial dependence plots, you should understand the algorithm behind them. And what it does is it iteratively sets all of the observations in each of the features to each of the unique values that are contained within that column. So over here, you can see in the original values in the income column, there's 5 different values. And so what we do is we set them all iteratively to, in this case, 20,000, and then 65,000, and then 108,000, and then 110,000, and finally 155,000. And we observe the impact that has on the correlation with the target. And so in other words, if I change, you know, this proves, like, if I move it to one, if I just moved it randomly to a value, I would be able to measure the impact that those changes had on the level of correlation to the target. But in this case, what I want to do, I'm interested in more than, is this an important feature? I want to know, what is the impact of each individual value upon that feature's correlation to the outcome? And that allows us, as we see in these graphs, to plot those responses. And so we have a good understanding of how the variance within that feature correlates to the outcome. And that gives us a lot of insight into why a decision was made. Say, like, okay, I didn't give you a loan because you only made $20,000 a year, and that's not enough to cover your expenses. And I didn't give it to the guy who made 65,000 for the same reason. But as soon as he went to 108,000, we saw that there was a strong correlation with being able to pay off the loan, and we started approving the loans. That's just completely a fabrication out of my mind. But this is how partial dependence works internally. We have another sensitivity analysis. We're probably running out of time, but this allows you to quickly identify non-influential parameters in situations where you need to be able to run computationally expensive operations to determine the level of influence of the remaining influential parameters. And it's based on a similar algorithm called permutation importance. And I touched on it in the previous slide, where I basically shuffle the values in each one of the columns, and I see how much it breaks the precision of the model that is produced or the accuracy of efficacy. There's a lot of different metrics, things like accuracy, precision, recall, F1, true positive rate, false positive rate, things like that. But basically, we want to know if the model becomes more accurate in its predictions or less accurate in its projections as a result of breaking the correlation between a specific feature and the target, the outcome. And so in doing this iteratively across a set of parameters, we can then stack rank the features by their level of influence. And then we can determine a cutoff, as we spoke of in MSA. And at a certain cutoff, we say these are not influential enough for us to bother examining further. And after the cutoff, these are influential enough, and we determine that we want to continue to analyze them more closely. And generally, I don't have one in here in my deck, but you'll use something called like a pipe stem graph, where you'll see a very sharp drop. And then once it starts to flatten out, as it moves through the feature set, you can see that the features have a steadily decreasing impact. And at some point where the curve flattens out enough, you just say, hey, the rest of these features aren't doing anything for me. They're just creating noise in my model. I'll stick with the first N number of features that are doing all of the heavy lifting towards getting, my accuracy or my precision or recall metric up to the level where, I think it should be. And finally, we're going to talk a little bit about Fairlearn. I know we spent a lot of time on the internal algorithms of Interpretable, and we're really kind of running over time, but Fairlearn allows you to mitigate the effects of bias that may be hidden within otherwise innocent or innocuous features. Now, if I had a loan application and I had columns or features for race and sex, I would look at that and say, I can't be determining whether or not I'm going to give somebody a loan based on their race, their sex, their age, their national origin, and a whole lot of other protected classes. So I'm going to throw them out right from the beginning. I'm not even going to ask the question, is there a strong correlation to the outcome? I'm not allowed to use that stuff. But what we'll find, as Mark Rubio did in producing Lime, that there is little biases hidden in the remaining data. Like, a person's zip code tells you where they live, and that zip code could be for public housing. And we know that we can decide that, well, they're probably poor because they live in this zip code. Or we could record their telephone number. And if it's NA, we can say, well, if they're not rich enough to afford a phone, then why would I give them a loan? Or something like that. And so what Fairlearn does is it allows you to root out those hidden biases and mitigate them using some algorithms to get around that. What they can do is flatten out the impact of those disparities in the model's predictions. And it does this with two primary things, and one of them is some custom metrics, and one of them is the selection rate that is specific to the Fairlearn package. And what it does is it assesses which groups would be negatively impacted by that model. Let's just say the selection rate is whether or not we choose to give them the loan or not. We may see a disparity between, let's say we included race. We would see a strong disparity between potentially one race and another. And we would say, well, that's not fair. We can't decide whether or not we're going to withhold opportunity to somebody based on something like that. So we'll pull it out. But then some of that information, as I mentioned, is hidden within features that otherwise appear innocent. So selection rate allows you to identify where these biases are occurring and work from there to mitigate those biases. And we do that with a couple of different algorithms, one being grid search, which is like a hyperparameter sweep. It sweeps through everything, and demographic parity, which flattens out that disparity or mitigates that disparity. And I know that was sort of a very quickly rushed explanation, but we are out of time. So I'll leave you with some resources. There's a book by Christoph Molnar, has been widely impactful to the development of a lot of these algorithms, and that can be found out there on his GitHub site. There are documentation and how-tos for both the Interpretable and the Fairlearn libraries, And I'll leave you with that. I'll forward a PDF of this deck to Tim so he can distribute that to you. And with that, that's the end of our presentation for today, and I hope you enjoyed it. It was really more about you understanding the Intuit and the concepts involved here rather than showing you a bunch of code. There is code, but it wouldn't help you understand why things are working. So anyway, with that, I'll give that back to you, Tim.
Hey, thank you so much for that great. Thanks for the great presentation. There's a question or two, and let me see. This was CC Rump. Can you speak to the use of both types of ML models, i.e. Glass and Blackbox together, to increase confidence in model prediction? For example, using Bayesian models to estimate uncertainty to neural network model or random forest model, uncertainty quantification can be used to evaluate predictive accuracy and build trust as shown in the literature.
Yeah, actually, we were talking about some of the interpretability methods for black box models inside the Interpretable package, and that's pretty much exactly what they're doing with things like Lime and Shap, and yeah, I think mostly just Lime and Shap, and I think that's really it. Those are the ones that are based on surrogate modeling, and where they're doing there is they are actually using these transparent models as surrogates for what's happening inside a black box model, and that's pretty much exactly what they're doing there. I hope that answers the question.
I believe so. Let's see. Yes, it does. Let's see. How does AML put this into practice? I know it's in GitHub, but can this be used automatically? Maybe this is a topic for ML Ops. Is that?
No. Actually, if you go out to Azure Machine Learning and spin up a compute instance or a compute cluster, generally speaking, you're going to find that both Interpretable and Fairlearn are probably already installed. If for some reason you find that the version that's being promoted on the GitHub site is newer than the one that's in that model, you can always update it just using a couple of lines in a Jupyter notebook, like bang pip install, and it will update it for you. But nonetheless, yeah, they're available for you out there. And if you're doing local model training, that is, you're building, a computer image on your local workstation and doing your initial development there, then you would be responsible for installing them yourselves. But again, on the resources slide, and you could probably just do a quick search on Bing for Fairlearn or Interpretable, and you'd find the GitHub sites. You could install them locally and do that work. So it is, for all intents and purposes, open source. You can do what you want with it. But to answer your question, it is installed by default on AML compute clusters and compute instances. And not only that when you're doing your training in your Jupyter notebooks, there are dashboards and visualizations that are associated with these packages that can be uploaded into your Azure Machine Learning workspace. So when you open up an experiment and look at the individual run, you'll see a tab across the top, one for explanations and one for fairness. And if you deploy these properly through code, and that code is available easily on docs.ml.microsoft.com and in the appropriate area under Azure Machine Learning documentation, you can upload those visualizations into the portal, so that anybody who's doing the ops portion of the ML or the ML ops lifecycle would be able to make those evaluations visually, looking at those dashboards.
All right. Well, I don't believe there's any other questions, John. Thank you for the very thorough presentation. You got a lot of positive feedback here. And everybody who is listening, I'll have the recording up probably by 3 this afternoon. I have some other meetings and stuff to do here, but I'll get it posted on YouTube at aka.ms Azure Cloud Events. Make sure to like and subscribe and all that kind of good stuff. But John, thank you, and we will see you in October, sir.
Thank you so much. It's been a pleasure. and I look forward to presenting for you again in the future.
Yeah, thanks, man. We'll see you in a little bit, and enjoy the Charlottesville area. I know we went there a couple. Have you been to Michi's Chicken? Hey, don't answer that. I'm sorry to ask that. I'll stop the recording, and thank you very much.
You're very welcome.